Hello and welcome to the lecture of mechanical vibration. In this session we are solving a problem of single degree of freedom free vibration, and we have to find the natural frequency of the given system. I am saying that this is a single degree of freedom vibration. So you can identify here that there is a mass connected with this spring, and the spring is connected with this bar. This bar is weightless and another spring is connected to this point, and this is a hinged joint. So if I will see, or I will try to visualize the motion of this system, if the mass is moving in the downward direction, there will be certain force at this end of this bar. The bar will also move, because this is a pin joint, so it is free to rotate about this point, and there will be certain extension or deformation in x1 spring. So finally, in such problem we are able to apply on either the Newton's approach, or we can apply the energy approach to finally get the equation of motion of this system. Once we will get the equation of motion of this system, we can identify the natural frequency of our system. So here I am showing the deformation, or the one of the condition of the system while the mass is vibrating. So if the mass has moved or displaced by an amount of x, the x will be combination of the deformation in this spring as well as deformation in this spring. And how we can identify this? That suppose deformation in top spring is x1 and deformation in the other spring is x2. So what is happening here? That this x is moving in the downward direction. So this end first, because of the deformation in the first spring, the bar will rotate and the bar end will come here. So this part is because of the deformation in this spring, and remaining is because of the deformation in this spring. So my total deformation x will be combination of these two values. We can also identify this by applying the superposition approach. Your superposition approach says that at a time you should consider only one spring, and remaining all spring will become a rigid bars. So in this case, this is my case 1, where I am assuming that this second spring will be as a spring and the first one will become as a rigid bar. So in this case, now this is a pin joint, but this is a rigid bar which is connected here. That means this bar cannot rotate now. So whatever deformation will be in the first spring will exactly transmitted to the deformation or displacement of the mass. So my x will be equal to the x2. Now for the second case, I am assuming that this spring has become now rigid and this spring will become now free. So if I am assuming that the deformation in this spring is x1, ultimately this end is directly not connected to in line with the mass. So what is happening here? If I will see this triangle and this triangle, these two are the similar triangle. So if this deformation is x1, it will be amplified here, and the deformation of this end would be L2 by L1 x1. This expression I got by applying the similar triangle. One triangle is larger one, this is the smaller one triangle. So my deflection or the displacement of this mass when there is a deformation is of x1 is here will equal to this value. So x will be L2 by L1 x1, and these two are the individual results. So my superposition method says that my total deformation will be the summation of these two values. So this is my first expression I calculated by applying the superposition law. Now second expression will be with respect to the force balance. So I know that if I will make the free body diagram of my bar, there are two forces acting at the bar. One is the K2x2 at this point, and another one is K1x1, because there is, if I will see the picture, there will be force in this spring and the force will be equal to the K1x1. The force in this end will be equal to K2x2. So these are the two forces. If I will take the moment at the pin joint, this length is defined by L1 and another length is defined by L2. So this would be my expression from the force balance. Now I have observed the one expression with the help of the superposition method. This is the second expression from the force balance. So now I will write my energy approach. Here this is my energy equation, where this is the total energy. I am assuming that the mass is moving, and at that moment the mass has moved by a displacement x. The velocity of the mass is x dot and acceleration is x double dot. So this is the expression for the total energy, half mx dot square plus potential energy in spring 1 and potential energy in spring 2. Now this will be the constant quantity because total energy remains conserved. if I will differentiate this term, I will get the one governing equation. But here, before I differentiate, I should replace this x1 and x2 in terms of x. So I know this is my equation 1, this is my equation 2. From equation 2 I can get x2 value in terms of x1, and then this x2 can put here. So this would be my expression for the x is equal to this value where I am having only x1. So first I will calculate the x1 from this equation. So this is the expression of x1. When I will put this x1 into this equation, I am getting the expression for the x2. So finally I have value of x1 and x2 in terms of x. I will put this x1 and x2 into this equation. So this is my final expression, which this is the total energy expression, and now I am having only one variable x here. If I will differentiate this with respect to time, so I will differentiate total energy with respect to the time and put to 0. So finally I am getting this expression. This is my final expression, and I know this is a simple harmonic equation which where this value representing the k equivalent. So this is my expression. If when I will rearrange all the term, finally I am getting that this is my expression, and my natural frequency will be k equivalent by m under root. So my expression for the natural frequency of this system will be this. Thank you.